Thank you for attending my talk, Expertise Breaks the Magic. Short-term memory is limited by long-term memory representation. Open most textbooks in cognitive psychology nowadays, and you'll probably read that the short-term memory capacity is fairly limited. Often you'll also read that this limitation is around 7 plus minus 2. This number is called the magic number, and was originally proposed by George Miller, who found that participants scored usually around 7 plus minus 2 in tests on their short-term memory. This number has been picked up by a lot of later authors, and there's been several debates about sort of the exact number in this sort of magical number. Quite famously, Nelson Cohen argued that it shouldn't be 7 plus minus 2 rather than around 4-ish. But does this magic number really exist in the way that we usually think about it? What actually influences this so-called magic number? Well, Everett and Kanawak did a quite famous study where they looked at how the visual complexity of stimuli influences the visual short-term memory capacity. Everett and Kanawak showed that as visual complexity increased, so too did the visual short-term memory capacity decrease. But what's going on here? What is actually influencing this so-called magic number? Well, Everett and Kanawak argued that this is due to the difference in the visual complexity of stimuli. They, for instance, argued that simple line drawings and Chinese characters are inherently more visually complex than Latin letters, and that is why there is this difference in the memory capacity. This is also further supported by the fact that several authors have tried to train participants on specific stimuli and found that, well, you can make people faster at recognizing or faster at detecting these stimuli, but you can't actually improve their memory capacity for them, seeming to suggest that there is some innate memory capacity on certain type of stimuli. But is that actually the case? Jackson and Raymond argued against this by showing that, well, Chinese participants were able to remember Chinese characters as well as they could Latin characters, which sort of suggests that, well, it might not be the objective memory capacity for items. This relationship between the physical complexity of items and the perceived complexity of an item, it was picked up by Sørensen and Kyllingsbæk, who conducted a change detection study using Latin letters and simple line drawings, similar to the simple line drawings used from Everett and Kanawak. What they quite interestingly did was that they looked at the Latin letter capacity and picture capacity at different age groups. So you had preschoolers, people second graders, fourth graders, and adults. And what they found was that the memory capacity for pictures stayed similar between each age group. However, the memory capacity for Latin letters increased as the participants got older. Sørensen and Kyllingsbæk argued that, well, what's happening here is very likely that the children, while they're learning how to read and write in school, they start learning these Latin letters, and they start creating mental categories for these Latin letters, and they keep strengthening these mental categories up to the point where they became hyper experts. It is therefore possible to improve this magical number through stimulus-specific expertise. Sørensen and Kyllingsbæk hypothesized that this is due to the fact that the children, while learning how to read and write, improve and create mental representation for the Latin alphabet. And this entire training that happens thereby further strengthens these categories, causing them to take up less space in the visual short-term memory capacity. But this does raise the possibility that this might just be something that happens in childhood, because we know that there are different stages of brain development. So, can this stimulus-specific expertise improvements, can we see them in adults? This was a question we posed when we extended results from Sørensen-Kyllingsbæk. We did this in adults at different levels of expertise, and also using a different paradigm to check whether or not the effects were still present in different paradigms. So what we did was, we looked at Japanese hiragana, because it is a thing that it is fairly easy to know whether or not people have trained with it or not. And we looked at participants at 3 different levels of hiragana expertise. People who did not know Japanese, people who were studying Japanese at university, and native Japanese speakers. And we did a whole report experiment, as seen up here, where the participants had to report all they saw. So, what do we find? Well, as you can see up here, we didn't find any significant difference between the 3 groups in the picture condition. Also here you might see that there is also doesn't seem to be any significant difference in the Latin condition, meaning that all 3 groups had a similar baseline of expertise for pictures and for Latin letters. Whereas there was a very significant difference between the 3 groups and the critical hiragana condition, with the novices being the worst, the trained being better, and the experts being the best. It seems to support the idea that people are able to create these mental categories and strengthen them in adulthood. Similar results have been found in other studies, where they also looked at expertise that is built up over a long period of time compared to the intensive training in previous studies. Of note here is a study series by Xian Shang, where they looked at non-language items, in this case familiarity with Pokemons. But this sort of begs the question, what's happening with the visual complexity as expertise increases? For instance, a lot of these items that have been previously studied, for instance Pokemons, are fairly visually complex. So what's happening? Why do we improve our memory capacity? We decided to want to study this, and to do that we looked to Chinese characters. Chinese characters are usually indexed by the stroke count, meaning how many individual strokes are in a character. This actually gives us a quite decent approximation of the sort of visual complexity of the individual characters. Furthermore, using the frequency of use, in other words, how often the character is used in writing, could give us a decent measurement for the familiarity with the individual characters. Dividing both in 2 gives us 4 conditions at different levels of sort of the visual complexity and the perceived complexity. Using these stimuli, we were able to conduct a whole report study on mainland Chinese participants. What we found was that the stroke count, or sort of the approximation of the physical complexity, didn't have any significant influence on the visual short-term memory capacity. However, what we did find was that the frequency of use, or the measurement for sort of the familiarity, had a very significant influence. This sort of suggests that the physical complexity of the item means nothing compared to our familiarity with them. A similar pattern was found by Conchi and colleagues, who looked at the visual complexity of familiar flags. And what they found was that the visual complexity of the familiar flag didn't influence the memory capacity at all, to the point where familiar flags as a whole group actually were as easy to remember as unicolored flags. Interestingly, when looking at the visual complexity of unfamiliar/fake flags, they actually found that in these cases, the visual complexity did have an influence. This would sort of seem to suggest that the short-term memory capacity is able to piggyback up on the mental representations in our long-term memory, actually to the point where the visual complexity of an item doesn't have any effect. This would also seem to suggest that if we have a magical number of items we can remember, it is highly dependent on the sort of long-term memory representations in our mind. Thank you for attending this talk. I'd also like to thank my co-authors as well as their laboratories and the funding agencies who has funded my research. Thank you very much.